Okay, welcome everyone to the last part of lecture 6. So we want to talk a little bit more about like censoring models, and a very popular type of model, or like one of the classic models, is the Tobit model, or in particular the Tobit 1 models. There's a couple of variations of this, and we will only discuss the Tobit 1 and the Tobit 2 model in this lecture. Yeah, so if you want to know more about this, the Wikipedia article is actually quite decent. So you can read that if you're interested. Okay, so like the classic Tobit model, Tobit, and sorry, comes from, of course, a guy called Tobin. Okay, let's maybe discuss first the name. So Tobit is a mix-up of the name Tobin, which is like the researcher that introduced this type of model, with Probit. This name, Tobit, is due to some rather famous econometrician, Arthur Goldberger. So he was kind of one of the leading econometricians in the 70s and 80s. Okay, so what happens in the Tobin model? So in the classic paper by Tobin himself, he looked at household expenditures for durable goods. Yeah, so for instance, whether you want to buy a new car, for instance. Yeah, so a car lasts for a couple of years. Therefore, when you look at this type of data, then you will typically see lots of zeros. Yeah? So there's many households that do not purchase a car in a particular year. Now, this can be thought of as some sort of censoring. So because maybe there is actually some sort of latent utility model going on in the background. Yeah, so kind of like this is the utility for purchasing a new car. And X contains variables such as the income or the household size and these kind of things. And you're only observing whether a household buys a new car or does not buy a new car, right? So you could think of this like when the utility of a new car, given like all the costs and all this kind of stuff, is positive, then this household purchases a car, and you observe like the actual value of the car, for instance, or the expenditure. Yeah. But if the utility is negative, for instance, like the family says the current car that we have is still good, yeah, and it costs too much, then the utility would be negative, and you don't observe anything. You observe actually zero expenditure. Yeah? So kind of this leads to a data set and where you have inflated zeros. Yeah, so kind of this is what you actually observe. As I said, kind of like you either observe zero when there's no expenditure on durable goods, for instance, a car, or you actually observe the true expenditure. You know? Okay. Yeah. So what do we do in this case? So first of all, something very important is here again we are making a rather strong distributional assumption. So we are saying that conditional on xit, the epsilons are normally distributed with some mean zero. That's not a strong assumption because as long as we include the constant regressor in X, epsilon having mean zero comes at no cost. That's without loss of generality. Yeah, but we say that there is some sort of variance. We will estimate this variance, but the important thing is that we truly make a distributional assumption. Yeah? So because we assume that the model error is normally distributed. Okay, so if this is the distribution of the model error, then keep that in mind. Then this whole thing here, the distribution of y(t) star, is of course the normal distribution with this as the mean and this variance. Yeah? So just keep that in mind. That's now, of course, important for finding the likelihood. Now, the likelihood depends on two parameters. Yeah? So that's the beta, that's simply the effect of each of the x's. And we have to estimate the variance. Let's define this indicator here, DIT, which is simply 1 if we observe something. Yeah? So kind of when we observe that the family purchased a car, and 0 if there's no purchase, for instance. Yeah? We make our life easy, as we saw in the beginning of the lecture. We always assume like IID data. So in particular, we assume independence. Therefore, the likelihood has this nice product form here. And yeah, well, if nothing is purchased, then we basically observe this part, right? So then kind of 1 minus DIT is 1, and DIT itself is 0. So this whole part here would be simply 1. And then we just observe like the CDF of y star at 0, because, well, there's now a point mass at the point 0 because we have that everything that is less than 0 is basically the probability is shifted into the point 0. Okay, now what happens from this line to the next line? Well, basically nothing. We're just plugging in some stuff, and we are using here the notation for the standard normal PDF and the standard normal CDF. And in order to do so, we have to kind of do some transformation. You see, for instance, here we look at YIT. Yeah, because we want to use the standard normal CDF, we have to kind of subtract the mean of YIT star, of the distribution of YIT star, yeah? And we have to scale this by sigma, and also on the outside we have to divide by sigma. And a similar thing happens here. So this basically from here to here, this is simply using the fact that you can transform a normal distribution with mean, mu, and sigma squared to something times the standard normal CDF. Yeah, so kind of that is a standard result. And well, then we simply take logs. Yeah? So all the products turn into sums. Yeah? And that's what you get. And now something important for computational issues is that this likelihood is difficult to see that this is concave. And we can make it concave by choosing a certain reparameterization of the likelihood. Yeah, so kind of instead of writing beta and sigma, we kind of choose alpha and h. Yeah, so and they're defined in a certain way. And simply by plugging in these values, you will see that well, this likelihood is now concave. Yeah? And as we've seen in the beginning of the lecture, concave likelihoods are nice because, well, if we maximize a concave likelihood, that means we will always end up with the global maximizer and not only with the local maximizer. Okay, now what would you do in order to recover the original beta and sigma? Well, I mean, you simply estimate the alpha and the h by maximum likelihood, and then you just plug in, you just basically do it the other way around. And this works because of the continuous mapping theorem. Of course, assuming that h basically does not converge to 0. Which of course is guaranteed because h is 1 divided by you know, the standard deviation, and the standard deviation has to be positive, otherwise it doesn't make any sense in the first place. Okay, so we can estimate this model by maximum likelihood, but instead of the maximum likelihood procedure, we can also choose to use the Hackett or the two-step Heckman correction. Yeah? Now, this is due to a super famous econometrician, James Heckman. He got a Nobel Prize already in 2000, and some people say he may get another one. And he has an insane amount of Google Scholar citations. Yeah? So this guy is really one of the leading researchers in econometrics. And one of his more famous papers, so he has, of course, a couple of papers that are pretty influential, but one of his papers deals precisely with this kind of censored data. And well, let's discuss a naive way of dealing with censored data. So recall that we have a lot of zeros, and we only have reliable observations when we have that the observed y is bigger than 0. Yeah? Because then the observed y actually corresponds to the unobserved y star, yeah? Which is actually the response variable of interest. Okay, now a naive econometrician would maybe say, okay, why don't we just then use only the data where we observe y bigger than 0? Okay, let's see what happens then. Well, if we take the conditional expectation of y only on this subset of data, yeah, then by definition, this is simply this thing, right? And now if we kind of plug this in the model, well, YIT star is simply defined as this plus epsilon, right? Yeah. Here, this thing doesn't depend on YIT star, so you know, the kind of conditional expectation here is simply the same thing, is simply that. Yeah? But here, what happens for the epsilons? Well, epsilon, of course, depends on YIT star because we can simply rewrite the model. Right? So kind of epsilon, we can simply rewrite this condition as this condition. Okay, now think about this. So if this model was supposed to work, we would need this part here to vanish. We would need this to be 0. However, this is clearly non-zero, right? So kind of recall that epsilon is a normally distributed variable. And definitely this part here will be non-zero. Now, we can actually say something about this. So there's a formula for, well, I mean, this is really just a formula. So let's quickly discuss it. Anytime you have a normally distributed variable with mean mu and variance sigma squared, then the conditional expectation of that variable conditional on that variable being bigger than some number a is given by this here. So it's given by the mean plus the standard deviation times what is called the inverse Mills ratio, this lambda thing here. So kind of lambda is defined as the normal PDF divided by 1 minus the normal CDF at x. That's the inverse Mills ratio. And therefore, if we go back, recall that epsilon was a normally distributed variable with mean xit prime beta 0 and variance sigma squared. So and then you should get this sort of expression here. Of course, in our case, our a is 0 because our data is censored at 0. That's basically our a. Okay, so this is what we get. So clearly this part is non-zero, and therefore the linear regression on only the positive data will give you inconsistent estimates. Okay, now what can we do? Well, the good news is that we know an explicit form of the distortion. So what can we do? Well, we basically we can correct this distortion. That is what we would do, right? That's a very simple idea. We know what is the bias, so let's correct it. Okay. Well, so how to write this as a model? So kind of in a model where we can only use the positive data. That's kind of like our goal. Well, first of all, we can always trivially write that YIT coincides with this conditional expectation plus UIT, where UIT is simply, well, the difference between YIT and the conditional expectation. And so that's trivially true. Now, by doing this, it's immediately clear that this thing here will have mean 0. And moreover, this thing here will have conditionally mean 0 by construction. Okay. Now, therefore, we can get a regression model. We can have a regression model where we only look at the positive data points. So this is the part that we always get. This is the part that comes. Sorry, this should actually be the UIT here. So it's not the original epsilon IT. Okay. Yes. So this is the UIT. Let me quickly check that. 1 second. I quickly correct that. Okay, let's run this. Okay, so now if you, in this model, running OLS on only the positive data points would actually give you consistent estimates, because this now acts, so this is now simply a parameter, and this acts as if it was just a different data point. Think of this as xit, and this would be some xit star, some variable. Now, the problem is, of course, that this data depends on unobserved parameters, like the alpha 0 is unknown to us. Therefore, this whole thing here is unknown to us. We cannot observe it. Now, what would you do whenever you don't observe something? Well, the answer is estimate it. And this is precisely what Heckman proposed. So the solution is to estimate this alpha using a first stage probit model. Now, why is it a probit model? Well, this comes precisely because we are looking at only the data points where we have YIT bigger than 0. And recall that this was precisely the definition of this DIT dummy. So DIT was 1 precisely when YIT was bigger than 0. And this is by definition, this thing is really just plugging in the definitions. And this is the usual way we arrive at the probit model. So really nothing fancy here. And this is also the simple, usual probit likelihood. So really nothing new here. So what we would do is that we estimate alpha 0. So this alpha hat is maximum likelihood based, of course, because we are using the probit model. And then we would only consider the data where the outcome is bigger than 0. And you see here, this thing is now observable because we have plugged in alpha hat instead of the original alpha 0. And by the way, again, this thing here is not the epsilon IT that we had in the very beginning. Let me just quickly change the name because, well, otherwise it may be confusing. So I give this a name UIT star because it's also, of course, not the same as UIT because, well, there is some estimation error in this step here, right? So kind of like estimating alpha hat gives some additional error, but that is sort of ignorable. Okay, now, again, what was the Heckman procedure? Well, we estimate the first stage using a probit. So that gives us like basically an estimate of the chance of observing y bigger than 0. And that is then used to kind of correct the bias that we would obtain if we were only to run OLS on the positive response data. That's the simple idea. It's a very elegant paper, highly influential. Okay, so some remarks are in place. Remember that kind of for this sort of thing here, when X was normally distributed, let's quickly take a look at the formula again. That depends on mu, but in particular, it depends on this inverse Mills ratio. So just keep that in mind for a second. And now, how does this behave depending on the constant A? Well, we can actually show that if X goes to minus infinity, then this inverse Mills ratio goes to 0. Which really means that there is no bias when A is minus infinity. Yeah, okay. Of course, here we are sort of assuming that we are looking at the mean 0 normal distribution, right? So kind of like if mu is 0 and this thing goes to 0 as A goes to minus infinity, then there's actually no bias. There's really, the expectation is simply 0. Okay. Moreover, we can say that if X goes to plus infinity, the inverse Mills ratio also goes to infinity. And it also goes so kind of like, you see the derivative is always positive. So we get an increasing bias. So the higher A, the higher the bias. And this also makes intuitive sense, right? So kind of like, if instead of 0, you have now 1 million as the censoring threshold, you of course have a higher impact of the censoring itself. So this makes intuitive sense because if you then kind of focus on the data that is larger than 1 million instead of the data that is larger than 0, it's intuitively clear that this should induce a larger bias. Because the data that you use is more selected in that sense. I hope this makes sense to you. Okay, so the Heckman procedure is used in the TOBIT1 model, but okay, sorry, there's a practical limitation that I should point out. And it's actually rather subtle. So notice that if we take the marginal effect of this conditional expectation here, we get beta 0k, so because we look at the kth component of X, times something that can be shown to be always positive. Okay, so you see, actually the argument here is missing something. So the lambda prime is never bigger than 0. So this part here can really be shown to be always positive. However, if I look at the marginal effect of xk on the probability of observing non-zero data, I also get something that depends on beta 0 times something that is always positive. Now, of course, the normal PDF is always positive, and sigma is also always positive. And so we see that both these marginal effects are proportional to the true beta. And now this can create problems in certain applications. And here's an example that, of course, is constructed in order to give you problems. Yeah, so let's say we are interested in the effect of age, and that plays the role of our XITK on life insurance coverage, which is our outcome. Now, of course, like there's, first of all, you will see if you look at the data set of a random subsample of the population, that there's a lot of people that don't have any life insurance. So now, what would you expect? First of all, older people are probably more likely to even have life insurance. Yeah, I'm not sure how many of you guys have a life insurance, but if you're 20, first of all, you don't think so much about the end of your life. And also, you don't have the money to put money on the life insurance. Or if you have the money, you like to spend it elsewhere. Now, however, once you condition on owning life insurance, yeah, so kind of this is really what we do here, right? We condition on owning some life insurance. Then, of course, the older you get, yeah, so the more X increases, the less attractive the life insurance coverage gets. Yeah? So kind of like the less life you have, what would you, why are you still insuring your life? Huh? So, therefore, here you would sort of expect that the true beta is negative. So here we get that the beta has to be positive. Here it's negative, and therefore we get a contradiction. So for this type of application, the Tobit model is like imposing conditions that are simply too strong. So this will yield a contradiction. So that's just a warning that you have to be a little bit careful about the type of application. Okay, now let's quickly also discuss the Tobit 2 model, which is probably even more famous. Yeah? So because here we model selection into the data set, basically. Yeah? So we have two equations. So there's a selection equation, yeah, which models whether an individual ends up in our data set, and we have an outcome equation. Yeah? So the outcome equation is like simply the equation of our interest. Now, this is again due to Heckman. So that's the kind of one of the famous applied papers that he had. See, he wants to kind of estimate the average reservation wage of all females, all women in the US. Now, this, of course, you see that this is quite old, and this type of question was popular back then. That's a kind of a female labor force participation was a hot topic in the 70s and 80s. Now, of course, here we don't really see kind of the reservation wages of the individuals. Now, the only thing that you observe is that if an employer comes and says, okay, I give you more money, so the reservation wage, what does it actually mean? Let's say you, for less than 10,000, you don't leave the couch. That's your reservation wage. Now, someone comes and says, okay, I offer you 15,000, yeah? And of course, you take the job because it's higher than your reservation wage. Okay, so that particular individual you would see in your data set because, well, that person would be working. Okay, now let's be clear about a certain point. So our sample only has women that are currently working. Yeah? So you only observe wages for people that are actually working. And you cannot simply say the wage for everyone else is just zero. This will bias your estimates as we just saw, right? Okay, so what does Heckman do? Well, he models the labor force participation decision. Yeah? So kind of you see that we have biased estimates because the people that are working, they self-select into working, and therefore these people may be structurally different from those people that decide to stay at home. Yeah? And therefore, whatever you find for the people that are working is biased for the general population, because this is not representative for the other people that stay at home. Now, yeah, so Heckman's idea is simply kind of to make this endogeneity explicit. So we explicitly model the endogeneity. Why do some people stay at home and other people go to work? That's the idea. That's a very simple idea. And yeah, so the Hackett approach is basically a sample selection approach. So for instance, let's say there's some variable X that has an effect on wage. And let's say your object of interest, the population that you're interested in, is only people that are currently working. Well, easy peasy. You take a random subsample of current workers, you get unbiased results. However, if you want to find out something about all people at working age, which is a larger population, then of course the current workers are not a representative sample because of the thing that I just explained, self-selection into working, and you actually have a sample selection bias. People self-select into your sample. Yeah, so you can think of many things, right? So for instance, let's say you have a voluntary job training on wage. This is kind of stuff that we have seen before. Yeah? And of course, participation is endogenous, self-selection problem, right? Therefore, kind of simply comparing the participants with the non-participants gives you biased estimates of the treatment. However, once you explicitly model the participation, you get unbiased estimates, of course, and this is like really important, provided that your model for the participation is correct. If your model for the participation is incorrect, then you will end up with some misspecification bias. Yeah. So oftentimes this, of course, entails strong assumptions. And therefore, nowadays, as we discussed before, many people rely on these natural experiments. That's kind of, you want to have a natural experiment that basically does some as good as random selection of people into working or non-working states. There is an ongoing debate between these structural models and this natural experiment literature, because while you have strong assumptions, typically you can also say more. So kind of, for instance, like because you have an explicit model of the sample selection, you can actually extrapolate from your sample more easily than when you have a natural experiment, where typically whatever you get is a local effect. Okay, now how does this work, like a little bit formalized? Well, again, we simply have two equations. This is the selection, so the first one is the selection equation, the second is the outcome equation. And here is the strong assumption. So we simply assume that the joint vector is jointly normally distributed with mean zero. Again, the mean zero is not the strong assumption. If these equations here contain the constant regressor, the mean zero assumption is for free. Here, we simply assume that here there's a normalization assumption in there, because if we don't normalize, if this was sigma 1 squared, then the whole system would not be identified. So there's an identification condition implicit here. And of course, this strong assumption is actually that we assume everything is nice and normal. And the normal distribution is the nicest distribution you can assume. And therefore, well, I mean, in practice, data is often non-normal. And then, of course, you would have misspecification bias. Okay, participation equation is that you say, so these are the latent variables, of course. Yeah, so kind of this would be the, whether the reservation wage is positive or higher, whether the offered wage is at least as large as the reservation wage. If that is the case, we observe a 1. That means yi star is bigger than 0, and otherwise we observe 0. Okay. The outcome is simply, what we observe corresponds to the true outcome whenever a person is actually in our sample, and well, we set it to 0 whenever a person is outside of a sample. Yeah, so kind of like the wage of non-workers would be set to 0 here, for instance. As we've seen, if we kind of do that and we don't take into account the sample selection, we get a bias. But as we did before, we kind of focus on the observations where we observe something positive. And as we've seen before, we would get this bias. Now, what is the Heckman procedure? The same as before. We use a progrit model to estimate beta 1. Then we replace beta 1 by beta 1 hat. So this whole thing here acts as if it was a data point, as if it was some variable. And once we have this variable observable, we simply run a regression on the data on basically our sample where we observe y bigger than 0, as before. Well, so pretty similar to the Tobit 1 model, actually. So again, this is a very elegant method. However, as we discussed, like this procedure is pretty sensitive to the distribution and assumption. So for instance, if this normality here doesn't hold, then you get, biases. In particular here, this kind of inverse Mills ratio is pretty sensitive. Because of the sensitivity, like the Hackett procedure is a little bit out of fashion. So nowadays, like the people like this natural experiments more, but who knows what the future brings. Probably it's kind of a unification of the structural and the natural experiment approach. Okay, so let's stay tuned, let's stay excited. That's pretty much it for this part of the lecture. I hope it was clear. I hope you enjoyed it. Okay, see you next week.